Hello everyone. Today we will be talking about sequence learning methods and what is this problem is and how do we use recurrent neural networks to solve sequence learning problems. Then we will look at the certain other improved architectures like LSTM and GRE. So sequence learning problems. So what is a sequence learning problem? The first question is, so suppose there is a vocabulary of only these many words. That is, the vocabulary contain the words like how, are, am, do, could, and so on. And now, let's assume the task is that given a word, the model or the network is supposed to predict the next likely word from this given vocabulary. So here, if we assume the first word to be how, then the next likely word in this vocabulary is are. So now for the sequence how are, the next likely word will be you, because like for example, even by intuition you can see it, though it is a very short vocabulary here, but among these many words, U is the most appropriate word to fill or to be present in the sequence after the word are. So if you fit now this how are you, the next likely word in this vocabulary is this question mark. So this is known as the sequence learning problem, where each word where the so if we look at this specific sentence, how are you question mark, the words are not independent of each other. The word are is dependent on how. The word you is dependent on the previous words it has seen so far. So this is known as sequence learning problem, where the next word in the sequence will be dependent on the previous words seen so far. So the inputs are correlated, they are not independent anymore. The size is not fixed. For example, in this sentence, the sentence can be how are you question mark, which has like four of the items of this vocabulary, or it can be okay, or it can be a longer sentence. Maybe let's say how are you doing, then question mark, and it can be a five word sentence. So the one of the issues with the sequence learning problem is that the input size is not fixed. And again, the number of outputs which are to be predicted is not fixed. So if you look at this problem here, and the task is to predict the next likely word, then in this case, we have predicted how many words, are, you, and question mark. But if it is a longer sentence, we might have to predict more words. So the number of output predictions to be made is also not fixed. The question which now arises is that can we solve this problem using CNNs, which we have been seeing so far in our lectures. So the issues with CNN is that it requires a fixed input size. So whenever you give an image, it is always of fixed dimension. And then if we give an image to a convolutional neural network, we get an output. Let's say we give an image of a dog, we get the output that, okay, the class is dog here. Now, next time if we give it another image, suppose cat, then it does not remember anything about the images which it has seen previously, so that its decision is getting influenced. That is, it will be independently identifying the image of class cat as cat. So the temporal information which might be there between sequence of words will be lost if we use CNNs. So now the sequence learning problem can also be of multiple types. For example, it can be one-to-one. So suppose we have simple fixed sized input and then we have to do this fixed sized output, which is something like image classification, and CNNs fit very well into it, that you give a fixed sized input to it, you get a fixed size output. So yes, you can then use something like CNN. The other possibility can be, which is now a sequence output, that you have a fixed sized input or you have one input, but the number of outputs to be predicted is unknown. it can be many outputs need to be predicted using single input. So this is a sequence output. For example, if there's an image and the task is to describe the image in a sentence, then the length of that sentence is variable. So that is the output, the number of words to be predicted. And that is variable. However, the input is a single image which is fixed. The other possibility is that the input is of variable length, but the output is fixed. That is many to one. So for example, in case of sentiment analysis, where a sentence or a big paragraph is given to you and you do not know the length or the number of words present in that paragraph, but eventually that given sentence or the text has to be classified into one of the known categories, like is it a positive sentiment, or is it representing some negative sentiment, or is it neutral, and so on. So then in that case the output shape or the output number of predictions to be made is fixed, but the input might be a variable. The more challenging scenario is when both input and output is of varied nature. For example, sequence input and sequence output. Suppose in case of translation, if there is a statement which says, "How are you?" and now this statement has the sentence has to be translated into any other language. Let's say in Hindi, "Tum kaise ho?" So in this case, the nature of the input is a sentence which can be of variable length of words, and the output is also a sentence in another language, but that can itself has different number of words. So here the input and the output size is not fixed. And the other possibility is many to many. That means, for example, synced sequence input and output, like video classification. Suppose there is a video, okay, and you give certain set of frames to the video, and you have to classify each frame. So suppose this is frame at time t, and you classify this frame at time t. Now the frame at time t+1 will also be classified, but its output will also depend on the previous frame. So this green arrow is modeling the temporal correlation here. So these are different types of sequence learning problems, and the problems where the size of the input or the output is not fixed is difficult to be modeled using CNN, 2D CNN. So for that, we then look at different architectures which might help us in solving these problems. The first architecture we are going to look here is recurrent neural network. It is mostly known as RNN. So this is how the RNN looks. So suppose x1, x2, x3, and xt are representing the input at different time steps. The subscript here is denoting the different time. So x1 is representing the input at time t equal to 1. x2 is representing input at time t equal to 2, and so on. y1, y2 up to yt is representing the output at that specific time. So if at time t equal to 1, x1 is given as an input, y1 is expected as an output. If at the next time stamp x2 is given as an input, y2 is expected as the output, and so on. So this is the problem here. This can be solved using RNN. So what RNN will do, that RNN will take this as input x1 and will predict it output y1. At the same time, it will capture the information about this input at time t equal to 1 in its hidden state represented by h1. At next time stamp t equal to 2, it will take the input x2. It will also take the input as the information it has saved from the previous timestamp inputs, that is h1 here, which is known as the hidden state information, and it will now take the hidden state and the input at time t equal to 2 to predict the output y2. Similarly, at time t equal to 3, it will take the hidden state h2 input x3 and will predict the y3. Now this h2 will be having the information about both these inputs x1, x2, okay, and so on. So this ht is known as the hidden state of the RNN at timestamp t, which can be represented as a function with parameters u and W, and this function depends on the input at that timestamp as well as the previous hidden state information. What it means that this H1 is depending on X1 and H0, input at same timestamp equal to 1 and the previous hidden state information. H2 will depend on H1 and X2, that is the input at time t equal to 2 and the previous hidden state information, and so on. The other thing is that the same parameters are used for all time instances. This means that for computing any HT, the same parameters U and W will be used, as well as the same function will be used. The only thing that will change will be this XT and HT minus 1 depending on the time we are computing it. So if you are computing at H3, it will be X3 and H2. If you are computing at H4, it will be X4 and H3. But the parameters U and W will remain the same. The function F will remain the same. So this is how we can represent RNN compactly, that we give an input X to the network, it predicts the Y, it stores some information as hidden state, and at next point, whenever we give an input, it will use its own information because it's a loop here, right? It's taking the information from the previous state as well to predict the current state or current output. So this HT, which we just saw here, this H0, H1, H2, and so on. So this HT is function of XT and HT minus 1 with parameters U and W. This is how it is being computed. So we have a matrix U and a matrix W and a matrix V. So this RNN will be learning these three matrices because it's a single layer RNN here. So the hidden layer will comprise of these two matrices U and W. And while doing the softmax, we will take the linear, so that is basically the FC layer being connected to the hidden state. That's why we have VHT, and then we will apply the softmax over it. So HT is being computed as the tanh function of UXT plus W times of HT minus 1. So U is the matrix and XT is the input at time t, plus W is another matrix which we will learn through the data in the previous state information HT minus 1, and then apply the tanh function over this. This will give the hidden state at time t. And YT will be, that is the predicted probabilities, will be the function of this HT. So softmax is being applied just to get the probability here. So softmax of V times of HT. So this HT is connected to another fully connected layer, on top of which we apply the softmax function. Now, the next question arises that, okay, how to learn this U and W and V? So to look at it we will be talking about these simple computational graphs. So what is a computational graph? Suppose there is a simple expression E is equal to A plus B into B plus 1. Okay? And so how will it be computed? We first need to store the value of A plus B into some variable C. Then we need to store the value of P plus 1 into another variable T. And then E can be computed as a product of these two variables. This computation can be represented as a graph shown here. This is known as a computational graph. And what will happen is that all these nodes will represent the variables, that is A and B, and the operations. So here C, D, E are representing an operation of this expression. So there are two addition and one multiplication. So the nodes in this graph will be representing these variables and these operations. So here A and B are the variables represented by these two parent nodes here. And then these two A and B will then be added together into another variable C. So this is one addition operation, right? This node is representing this addition operation. Similarly, B is also added 1. Now this one is a constant. There's no other parent, just B here, because this operation is depending only on the variable B. This addition operation was depending on variable A and B. both. So this node will have an edge from both these nodes, node A and node B. The next is product of these two additions. So C is equal to A plus B equal to B plus 1, and then the product of this will give us the final expression E. So E equal to C into D. Now this depends on variable C and D. So C is here, D is here, and there will be an arrow from C to E and D to E. To see how this is worked, let's give a value to variable A and B. So let's say A is 2 and B is 1. So C will get a value of 3, B will get a value of 2, and E will get a value of 6. Okay. So we'll start from here and we'll keep on following the arrows and moving upward. So this is how any computation can be represented. The next question is how to use this graph to compute the gradients. So let's compute the gradient for each edge, right? So this edge shows that this node is dependent on the previous one, right? So if we compute the gradient of C with respect to A, it will be 1. Here, gradient of C with respect to B will be 1. Gradient of D with respect to B is 1. Gradient of E with respect to C is D. Okay. And gradient of E with respect to D is C. Remember. Okay. So this 2 and 3 is there, but this is because the value of D is 2 and the value of C is 3. So that's why we have 2 and 3 here. And divided C by divided A here was nothing but 1 and so on. Okay. So now we have computed the gradient for each edge in this graph. So to get the gradient of E with respect to the variable A and B, these gradients computed for each edge has to be merged. Okay, so now we are supposed to merge these gradients computed per edge to get the gradient of E with respect to C, with respect to A, and with respect to E. So how we will do that? The general rule is that if you have to compute the gradient of E with respect to A, reach the node E starting from A by all possible paths, and across each path multiply the gradients and sum it over all the possible paths from A to E. So gradient of E with respect to gradient of A. So what is the path from A to E? That A to C to E. Okay, this is only one path from node A to the node E. So what will be the gradient of E with respect to A? It will be delta E by delta C into delta C by delta A. And that will be 2 into 1, which is equal to 1. So the product of the gradients computed for each edge. Now, let's compute the gradient of E with respect to B. So start reaching the node E, starting with node B. So the node E can be reached if we go from B to C and C to E, as well as B to D and D to E. So there exist two paths starting from node B, ending at node E. So the gradient of E with respect to B will be the sum of the gradients across these two paths. Now, the gradient across this path will be product of these two values. So it will be 2. The gradient across this path will be product of these two values, which will be 3. So the total gradient of E with respect to B will be the sum of the gradient across this path plus and this path. Right? So that will be 2 plus 3, which is equal to 5. This is clear how this computational graph is working. Now, similarly, computational graph can be constructed for RNN. So how this RNN will look like? So here, x1, x2, x3 is representing the inputs. y1, y2, y3, yt, and so on is representing the predicted output. This f of uw is the same function with the same parameters u and w. So sorry. So what is happening here is that when we give an input x1 to this network RNN, it will take the previous hidden state, use these parameters u and w to compute the function of x1 and h0 to predict h1. And when it will predict h1, or it will has the hidden state information updated, it will use it to predict y1. And depending on how close this y1 is to the desired output, the loss will be computed as L1. Similarly, for the next input x2, it will take the previous hidden state information h1, use the same parameters u and w to compute the function of x2 and h1 to get h2, which will then be used to predict y2. Depending on how close y2 is with respect to the ground truth value, we will get the loss value L2. So this is, so if we have to compute the gradient for this RNN, then it will be equal to the sum of these losses, that is L1 plus L2 plus L3 up to LT, with respect to what are the parameters here? The matrix U, the matrix W, and the matrix V, which is converting, by which we are getting Y1 from these hidden states. Okay, so these computing gradient of the sum of these losses with respect to the parameters of the RNN here, which is the parameters of RNN is U and W, and the parameter of the fully connected layer here will be V. Remember this V here, this V. Okay, so computing the gradient with respect to U, W, and V will help in updating these parameters so that this RNN model is being learned on this data set. Okay, let's look at a small example here, which is this character label language methods. This is a very small example and just shown for explaining the concept in detail. Suppose there is a very short vocabulary of only these 4 characters, H, E, L, O. And the task is that we have to predict the next likely character. Given a character, the next likely character has to be predicted. Okay. So starting with H, the character H, it will take it into an input layer. So the input layer will be represented as a one hot encoded vector of length of the size of the vocabulary. The size of the vocabulary here is 4. So each input vector is of length 4. H, let's also assume that H is given the index 0, E is given the index 1, L is corresponding to the index 2, and O is corresponding to the index 3 in this vector. Okay. So for encoding H as one hot encoded vector, it will be represented using this 4-dimensional vector with 1 at the 0th index, indicating input character to be H. Once we get this as an input character, there is this hidden layer. Okay, so the hidden layer is 0.3 minus 0.1 and 0.9. Okay, and whatever is this hidden layer, we will multiply it with the V and we will get the output, that is V times of HT. And suppose we get this as the 1, 2.2 minus 3.0 and 4.2. Once you apply the softmax, the maximum probability is for the second element in this vector, which corresponds to the letter E. So the predicted word is E. For the next time, we will give this E as an input to the model here. So here we will have E. It will be represented using this vector with 1 at the second, with the second element being 1. Then this previous hidden state information and this input corresponding to character E will help in updating the hidden state information, which will finally give into this output, and applying softmax, the probability of the character L is given the maximum. So the next character predicted is L. Similarly, L will now be taken as an input by the model, represented by making the third element of this vector as 1, using this input character L and the previous hidden state information to update the current state hidden state information, and this hidden state will then help in predicting the next word and that is again comes out to be L, because the probability is maximum corresponding to the third element, which represents the index corresponding to the letter L. Again, this L will be given as an input, and similarly, following the same procedure, we will get the output O. So this is how this is a simple character label language method where we are giving each character as an input, and the output should be the next likely character to be predicted. Okay, so this is exactly what we saw just one slide before, and now how this will work is being shown here. So here the loss will be computed after this softmax layer. And what will be the loss here? Can anyone help me answer what will be the loss here? So if you notice here, the task for each character is a classification, right? Given what is the most likely character from this vocabulary, right? Or which is the character which should be predicted next, similar to the classification task, right? One out of many possibilities. And what is the loss function we use for classification? It is nothing but negative log likelihood. So here the loss function will be the negative log likelihood of, so it will be the negative of log of 0.84. Here the loss function will be negative of log of 0.5. Here negative of log of 0.68 and so on. So these all loss terms will then be summed together and will be used in updating the parameters of this network. So recurrent neural network are really good for solving these sequence modeling problems. However, there are still certain issues with RNN. The first issue is that it suffers from short-term memory and has vanishing gradient problem. What it means is that if the sequence of the characters is too long, then the network will have hard time in remembering the information from this information of the input which was given way before. For example, if this sequence here HELL, but if this is a very long sequence of let's say 1000 characters, then the network will not be good at memorizing or remembering the information from the starting 100 characters. So this is known as short-term memory. That at each point it is just able to remember very few recent inputs. So how to rectify this? One thing is that instead of using 10H here, which was resulting in this vanishing gradient problem, we can try using gradient. We can do better with normalization, use certain kind of regularization over the weights, use short sequences of words because that is what it is good with, right? However, the better option is that maybe we should look at more sophisticated architectures to solve this sequence modeling problem. And in this talk, we will be looking at one such architecture known as long short-term memory, or LSTM in short. So this long short-term memory, LSTM, is also useful in solving these sequence problems. It is long short-term in the sense that it does not have hard time in remembering the longer dependencies here. For example, suppose there is a sentence that I went to France, but I was not familiar with, or I was not able to understand French. So here this French and France have correlations, right? They are dependent on each other. But what will happen with RNN, it might not be able to capture such long-term dependencies, but with LSTM, this will not be an issue. So how we design this LSTM? So this here represents the architecture of LSTM. It will have couple of gates. So initially we saw that similar to the RNN, it will also have hidden state, it will also have an input, and it will also predict the updated hidden state, HT. So XT, HT minus HT is similar to what we have seen for RNN. However, it introduces certain gates which will help us in maintaining this hidden state information according to the input. So what I mean here is that there is some cell content. So along with this hidden state, there is also one extra information being maintained, which is known as cell content. And this cell content is keep on updated as we go on processing the inputs. And the update of the cell content depends on the output of these forget get. The forget get tells the network how much of the information should be retained from past and how much of the information from the current should be used, maintained. Okay. Similarly, we have this compute the input gate here, this, which will be helping in retaining the information from the current input into the cell state. Okay, and that will help in computing the new cell content. And the final cell content will be some combination of the previous cell content and the current new cell content. And this ratio will be maintained by the output of this forget gate. Okay, the output gate here will help in maintaining the balance between the so this output gate is what? So this is depending on this XT, right? So this output gate here will ensure that how much of the current input should be accounted while predicting the output here. So that is why we have this OT here. So we will get this OT, we will take this HT, and we will do the sum, and then we will predict the final HT here. Okay. So introducing these three new gates, that is the forget gate, the input gate, the output gate, and the new state, which is known as the cell content here. So these are the four new terms added to the RNN to make it more reliable for long-term dependency, so to make it able to handle the long-term dependency. So here is a brief summary of how this LSTM looks like. So we have this FT representing the forget gate. Here we have all these sigmoid functions. There we have the tanh functions, but here when we are representing the gate, we are using the sigmoid function. The reason is that it will always give you a value between 0 and 1. And that can be seen as the ratio of the value which has to be retained from the past and how much of the value from the current should be used while updating it. So forget gate controls what is kept versus what is forgotten from previous cell state. It depends on the previous cell state, HT minus 1, that's previous hidden state, and this is the biased term. Okay, so the previous hidden state and the current input will decide how much of the content should be maintained or should be forgotten. Similarly, input gate here controls what part of the new cell content are written to the cell and how to compute the new cell content. So it will be a function of xt and ht minus 1. The output gate will control what parts of the cell are output to hidden state. So that will again be a function of ht minus 1 and xt, but with different parameters wo followed by a sigmoid here. So now once we have computed these values ft, it, and ot, how they will be used. So here are these three equations where these information of these gates will be helpful. So CT tilde represents the new cell content. That is the content which should be written to the cell based solely on the current input xt. Okay. And the final current cell content will be some convex combination of the new cell content and the old cell content. So CT minus 1 is the old cell content, CT tilde is the cell content computed with respect to the current input, and the final cell content is some combination of these two inputs, which is being decided by the output of the forget gate and the input gate. Similarly, HT, which is the hidden state here, this it will be depending on the current cell content, but it will again be controlled by the output of the output gate. So this way, because of this forget gate here, the cell content is getting updated, but according to the output of the forget gate, which depends on the current input and as well as the previous hidden state, thus ensuring how much of the previous cell content should be retained and how much of it should be forgotten. Similarly, for computing the hidden state information of the cell, it is depending on the output of this output gate as well as the current cell content. Okay. Okay, so now with this, because we are falling short of time, let's look at the implementation of recurrent neural network in PyTorch. So, so here is this recurrent neural networks (RNN), and we will be looking at their implementation in PyTorch. So, first of all, we need to create a vocabulary. Suppose we are given this text, okay, and these are the set of sentences which are available to us, which will be forming our data set for now. So first of all, we need to get each and every character separated from this text. So all the set of list of characters which are present in it. So that can be created using this this line, executing line 4 will help us in getting these characters and then enumerating them and converting into dictionary. So now and then again, so what will happen here that we are trying to create a dictionary where each character will map to one unique index. So if we print this dictionary here, we will see that the character F is assigned an index of 0, character T is assigned an index of 1, character O an index of 2, and so on. So this vocabulary is of length 70, okay, and each character has been assigned an index. Okay, and if we try to look here, so this is how we have created the vocabulary, the set of all the characters which will be present in our vocabulary, and the set of characters which the input will always be one of the characters from the set, and the output at any point will also be one of these characters. Next step is data preprocessing. So here the string can be of variable length, right? For example, this hey, how are you? The number of characters are different. Here, good, I am fine. This has different number of characters, and so. So for that, to make sure that we get similar fix, what we'll do we will pad it. So we'll make sure that each input has the same length, that is the same number of characters. For that, we have computed the maximum length, that is the maximum length of any sentence here, and then we will make sure that each sentence now has similar length by adding white spaces at the end. So this is a simple loop which will loop through the list of sentences and add a white space until the length of all the sentences matches the length of the longest sentences, which is 15 characters here. Now, the next step will be to create a list that will hold our input and target sequences. Okay, so what does that input sequence and output sequence, target sequence means? In case of input sequence, we will be giving each character and we will be expecting the next character. So here it will be like, so we will, if we give H, we expect E. Then we will give E as an input, we will expect Y, and so on. However, the last, so here in this sentence, hey, how are you? Once we have given O as an input, the output predicted will be Q. And there is no more further input to be given to the sentence. Okay, so that's why the input sequence is the entire sentence except the last character. So hey, how are YO? Similarly, good, I am fine, and there was a dot which has been drawn, and so on. Okay. The target sequence, however, is different. In case of target sequence, we will be starting with predicting the next character, right? So H will always be given as an input, and the first prediction will be with the character E. However, the last character to be predicted will be the last character of the sentence, which will be U. Okay, so this is how it will work. So this is clear, right? How we are creating the input and target sequence here. Okay, so once we have created this input and target sequence, what we will do is that we will convert them into one hot encoded vector. So remember this figure which we discussed just. So remember this, that each input H, each character will be represented as one hot encoded vector. So the same thing we are trying to do here. What we are doing is that once we have done the padding and we have created this input sequence and target sequence, we are now representing each character by a one hot encoded vector. Okay. So what will be the shape here? the size, the batch size, this length of the sequence, which is here how many? 14, and the one hot encoding size, which is 70. Remember, each character will be represented as a one dimensional vector of length 17 because 17 is the size of our vocabulary, and exactly one of those element of this vector will be 1, representing the presence of that specific element. So, and this 14 is representing those 15 characters in that sequence. So it's the 14 characters in that sequence because the input sequence is one less, right? And then this input shape here 3 represents the batches because we have 3 sentences here. Okay. So once this input has been processed, we will now define the RNN model. So how to define the RNN model? A simple model has been written here. This RNN layer is being given, is already present in the torch.nn package, and from there it has been inputted. The hidden dimensionality will be the dimensionality of the hidden matrices U and W, right? That will be defining the size. So it will be defining the size of U and W and the number of layers. So right now we are just working with one layer, and then a fully connected layer, which will be operating on top of this hidden output. That is the V we have seen before, right? So this V is represented by this self.fc here. So, and what we will do, a simple forward pass will be done. So for each forward pass, we need to know this H. What I mean by H here is this hidden layer, right? So even for this initial input H, we needed some hidden layer, right? Maybe this figure will explain more. So even for this input X1, we needed H naught. So that's why what we will do is that during each forward pass, this hidden layer will be initialized. So this init hidden will initialize the parameters, the hidden state with this 0. Okay, and then a forward pass will be computed. So we will just do the self.rnn of x, where x is the input here, comma hidden, which is the hidden state information here. And then once we have done this, we will get the output of the hidden layer, and then we will apply pass it through the FC layer as an input and get the output. And applying the soft mix on out will give us the final probability of the most likely character. Okay, so instantiating the model here, defining the number of epochs, the learning rate, defining the loss, optimizer, and so on. Training it. So for training it, we will do the forward pass. Okay, we will do the compute the loss. Loss will be nothing but the cross entropy loss between the output and the target sequence, which we have already created here, which will also be represented as one hot encoded vector. But here, instead of that, what we will do, because it's just a cross entropy loss, so you can just even pass the index of the character and then compute the loss and then optimize the stack. And this is how the model will be trained. Okay, so the model has been trained. So, and now the task is to predict these scores. So let's test it. Test this model which we have just trained. So for that, suppose we have to predict it. Okay, so for prediction, what we will do is we will first include the character. Okay, we will give it as an input to the model. We will get the probability of the next likely character to be predicted, and we will select the max of this probability vector. And the max will give you the index of that character. Using the dictionary which we have maintained, we can retrieve the character which should be predicted, which will be corresponding to the index CHARINT. Okay, this will be representing the index of the most likely character, and this index will be used to retrieve it from the dictionary. So here is it. Let's say we want to predict it. So suppose we will be giving this good as an input, and now we want to predict how this model will behave. Okay, so model.eval start is equal to start.lower, so it will convert this string code to a lower string. Then for each character in this start, we are creating a list of characters. So it will be, what will be the case here? It will be G, O, O, and D. It will be a list of 4 characters. Okay, and size will be output length. So let's say we want to predict these 15 characters next. So this output length minus length of characters, which means how many more characters needs to be predicted? 11 more characters to go. Now pass in the previous characters and get a new one. So for II in the range of size, so we are predicting next 11 characters here. Predict model, comma, guess. So pass. What we will do, we will call this function predict here. Sorry, yeah, the function predict here. We will pass the model as an input and the guess, which is this. Now this guess will try to take the last character and will give it as an input to the model and will return the most likely character to be predicted with hidden listed edge. We get this and we'll append it further to guess and we will then again use it to as an input to the model. So this is like a loop here, right? The model predicts something that becomes an input to the model, then model predicts something that again becomes an input to the model and so on. And let's try to, and here the output should be printed. So we are then printing the output of how it looks like. So when we do this return join.char score, this is how the model is returning. Good, I am fine. So good was given as an input and the model has predicted I am fine here with the spaces as well, right? Okay, so this is a simple tutorial on recurrent neural network where we have implemented a character level language model with this as the vocabulary, this as the training data set, and the model has been trained and the model is doing pretty good here. That given this good as an input, it is able to predict good, I am fine. Okay, so now